Now I want to talk to you about synthesis and decomposition reactions. This is the subject matter for chapter 10. And we've got a couple of kind of reactions. In the balancing chemical equations, when I already talked to you about the combustion reactions where you have hydrocarbons that are being burned in oxygen. Alright, so that's one type of reaction. Altogether we have 5 types. Synthesis and decomposition. Synthesis, what you usually see is you see two things. Can be an element plus an element. You can also see some compounds plus compounds, and then they get together. So if you want to think about this in terms of human relationships, you have the two individuals on the left, and they combine to form the happy couple on the right. Now, the other, or opposite of this, is when you have a single thing on the left side of the arrow, and it breaks down to give A plus B. And now, again, in human relationships, we see this too. You know, one minute you see the happy couple hooking up, and the next minute, oh well, not so happy anymore. So the bottom line is, when you look at synthesis and decomposition, synthesis, the getting together, decomposition, the breaking apart, and hopefully you can look at this and say, I wonder if these are opposite or can be opposite processes. And they are. So that's something you want to think about as we're going through this. Now let's get into some examples. Here's synthesis. We'll start with synthesis. And it says hydrogen and chlorine are reacted together. And this is going to look a lot like, say, test questions. Now hopefully you can see synthesis. There's element plus element. When two elements get together, they're the simplest thing you can have. And they get together to form a compound. So let's see. We have H plus Cl. Now we have to remember that hydrogen and chlorine are both diatomic. And you have to think, well, if they get together, what are you going to form? Well, how about just plain HCl? Alright, so it's actually the reaction yields hydrochloric acid. And to finish balancing the equation, you put a 2 up there so that you have 2 hydrogens, 2 chlorines on the left, 2 hydrogens, 2 chlorines on the right. And you have to kind of see this, you know, elements are the simplest thing. So when they get together, they're going to form some kind of compound. And hydrochloric acid would be obviously a pretty good candidate for that. Now the next one of these, we did this in class. And when it says burned, when you take something like an element and you burn it, you have to kind of think, well, what's going on? You know, the atmosphere's got a bunch of oxygen in it. All right, so as a result, when you take magnesium and you add oxygen to it. So when you see burned, you should be thinking add oxygen. You could call it a combustion reaction. In this case, I'd like to keep combustion to hydrocarbon combustion. And I'd like to say when you see two elements getting together, like in this case, I'd prefer to call it synthesis. Anyway, so what's going to happen? You burn this stuff. It's a very, very, very bright flame. It'll actually even burn the retina if you stare at it too long when you're doing this. But magnesium and oxygen, let's see. Magnesium forms a +2 cation. Alright, and oxygen forms a -2 anion. So those guys are going to cancel out. So the compound that you get is just going to be magnesium oxide. And then you notice here your oxygen is diatomic. So because it's diatomic, you have to put a 2 there and a 2 there, because you want to finish this thing by balancing the equation. So 2 magnesiums on the left, 2 magnesiums on the right, check. 2 oxygens on the left and 2 oxygens on the right. So we have a balanced equation. So we're done. So, you know, again, synthesis, 2 things getting together. Usually it's the simplest things, such as elements, 2 elements getting together. Now you can also have a different class of synthesis reactions where you see a compound getting together with another compound. All right, so hopefully you guys can look at that and see magnesium oxide plus carbon dioxide. That's 2 compounds getting together. Later we're going to be studying this thing called a double replacement reaction, where the cations and anions swap with each other. But if you did that here, you'd just end up with the same thing you started with. So when you see something like this, what I want you to think is patterns. And the question you should be asking yourself is, when I see carbon dioxide, what is the only polyatomic ion that we've been studying that has carbon and oxygen in it? And the one we've been studying is the carbonate ion. So, you know, what I would say is write carbonate over here. Now, you know carbonate's going to be -2, Magnesium's going to be +2, and so those cancel out to give you magnesium carbonate. Now let's go back and have a quick look. Let's see, I see a magnesium on the left, magnesium on the right, check. A carbon on the right, a carbon on the, left, a carbon on the right, check. And I see 2 oxygens here, 1 oxygen there, so 3 carbons on the left, oxygens and 3 oxygens on the right. So this is balanced. So guys, again, when you see this, look for patterns. You see carbon dioxide, I want your brain to be thinking carbonate, especially when you suspect a synthesis reaction. The next one is pretty hard, okay? You have to look and see Na2O is sodium oxide, and it says reacted with water. Again, as we get deeper into this, and obviously we've done this in class, this is more for review for you, but when you see water on one side of the equation, well, first of all, you might think, well, compound plus compound, this has got to be some kind of double replacement reaction. If you try that, you get the same thing you started with, so it's not going to be double replacement. So you got to see and look at it carefully and say, what is the only polyatomic ion that I've been studying that is related directly to water? And the thing I think, in my brain anyway, when I see that is I think the hydroxide ion, OH-1. And so therefore, when I see this kind of reaction, this plus water, I'm going to first suspect double replacement, but I don't see it, so the only other choice I've got is synthesis. And then I'm thinking water on the left, hydroxide on the right, so I'm just going to say, all right, sodium hydroxide. Sodium hydroxide. So there you go, right, sodium hydroxide. I notice if I put a 2 over here, that will balance off the equation. Let's just check it. 2 sodiums, check, 2 sodiums. On the left, let's see, I see an oxygen, so 2 oxygens on the left, 2 oxygens on the right, 2 hydrogens on the left, 2 hydrogens on the right. I am balanced. So that's how you do that kind of synthesis. This one is a little bit harder. And so I want you to just think patterns when you're faced with this kind of stuff. Let's look at the next one, decomposition, decompose. That means something is going to break down. One thing you might see is when you see one thing on the left-hand side of the arrow, it's got to get to something simpler. And electrolyzed, lysed from biology last year, means broken apart, electro by electricity. So you're basically taking water and breaking it down. That's how you know it's decomposition. All right, and so sometimes you'll see electricity or something written on over the arrow to tell you, what am I going to get out of this? I know I'm going to get hydrogen, I know I'm going to get oxygen, and I know these guys are diatomic. So let's see, because I have 1 oxygen over here and there's a 2 over there, that means I have to have a 2 and then a 4 to make, wait, what did I do? Not a 2 and a 4. Hello. 2 and a 2. That's more like it. Alright, so I have to have, let me just go back and check it. I've got 4 hydrogens on the left, 4 hydrogens on the right, 2 oxygens on the left, 2 oxygens on the right. So I am balanced. So you notice this is a compound breaking into the simplest things it can break into, its elements. A real good, let's say, indicator for this kind of decomposition reaction. Let's look at the next one. Potassium chloride is electrolyzed. I got one thing on the left-hand side of the arrow. Well, what can I make out of this? I can make a K and I can make a Cl. Got to remember that chlorine in its elemental form is diatomic. It's going to force a 2 on the left and a 2 there. So now I've just finished that reaction. So again, decomposition. Look for one thing on the left. Now there's also a little bit harder type of this. This is copper 2 carbonate. But, my dead giveaway, heated, well, that's one way you can break stuff down. If you've ever been in the kitchen and gotten a little too warm with the macaroni and cheese, you know what decomposition's all about. So anyway, I look on the left. Oh, I see carbonate. And just like in the opposite, which is synthesis reactions, I said if you saw carbonate on the one side of the arrow, what are you going to look for on the other side of the arrow? I'm thinking carbon dioxide. Write it. Okay? And then you say, all right, if carbon dioxide's on the right, I have 1 C and 2 oxygens that I'm going to take away from this. Then the question is, what do I have left? Well, I've got copper oxide is left. Now you can go to your troubleshooter guide and it's going to say metallic carbonates decompose to give a metallic oxide and carbon dioxide. But guys, look for the pattern. Carbonate left, CO2 on the right, you write it and then make it work. This is a really, really good way to handle these problems. So see the pattern. There it is. I'll just do it one more time. CO3 on one side, CO2 on the left, or excuse me, on the right, and then, what do you got left? You got a copper oxide. This is the one, by the way, we did in the lab. The copper oxide was a black powdery material, and the CO2 is what we used to put out the splint, the burning splint when we did that reaction. All right, let's look at our next one. And it's going to be potassium chlorate, KClO3. Now, if you're having trouble with your polyatomic ions, you got to know what chlorate is at this point. But anyway, this reaction is the one we did with the gummy bear. Now, we heated it up. I melted it in the fume hood, if you remember. Then we dropped the gummy bear in there. Because you have a certain thing present, that gummy burned like crazy. And when you think about that, you say, well, what was causing that gummy to burn as well as it did? I mean, my gosh, it was just a little gummy bear. Well, things burn really well, and what do they need to burn? They need oxygen. So what I'm going to do is I'm going to write oxygen. I'm looking for my patterns again. I see chlorate. Think oxygen. Why? Because the gummy bear burns so brightly. All right, and then I'm going to say, okay, if I get rid of my oxygen over here, all right, well, what's left? Well, then the other thing that's left is going to be potassium chloride. Now, obviously, you didn't quite get rid of that. I mean, the O3 was still there, but you can take your thumb and cover up the oxygen, and you say, hey, I got KCl left. And then now the only thing is back to balancing the equation. So I see a 2 over here and a 3 over here. Least common denominator is 6, so I'm going to need a 3, a 2, and I think a 2 there finishes it. So that's how you do that decomposition. You've got to look for the patterns and spot it. I see chlorate. I know the gummy bear burned brightly. I'm going to write oxygen. Cover up what's left with my thumb or whatever. I see KCl as the other product, and then balance it. So that's really the process that you want to follow for these things. Finally, this one's a little bit harder. NaOH is heated. All right, we can put heat over the arrow. Again, I see one thing on the left. It's got to be decomposition. And what did I tell you? When you see hydroxide on one side, what are you looking for on the other side? I'm thinking water. H2O. And here, this is a little harder, but you got to kind of think ratio. I see here I have 1 oxygen to 1 hydrogen. Here I see 2 hydrogens to 1 oxygen. So that means there's got to be an extra oxygen left over here. And I'm going to make sure, sodium's +1, oxide -2. So I'm going to end up with this thing going on over here. I believe I need a 2 there. And now I'm going to start counting. I see 2 sodiums, check. I see 2 oxygens, 2 hydrogens. 2 hydrogens there, and an oxygen. So I am balanced. So that's how you do it for that last one. This one is harder. Okay, it's harder. Why? You have to see one thing on the left and on the right. The thing people have the hardest time with is thinking that it's going to be an oxide, a metallic oxide on the right. Use your troubleshooting guide if you have to memorize it. And remember now, this is showing the decomposition in this direction. Okay, but if you were given sodium oxide and water, that would be the synthesis in the opposite direction. All right, so just kind of think and look for patterns. You will be able to succeed at this, but it's going to take some practice, which I know I've given you enough worksheets to do. So that's synthesis and decomposition in a nutshell.